Right. It's time for us to get started. Happy Friday. I can tell that it's our work day because there are significantly fewer people here than usual. But you all made the right choice. Sorry to those who are watching this back and are now offended. So the problem that we want to now solve kind of in general, but be able to supply an answer for Project Euler is the prime factors of 13,195 are 5, 7, 13, and 29. We want to figure out the largest prime factor of some number that an integer can't even store. What is that number? Anyone know that off the top of their head?
2 billion, right?
So we have
Oh, is that?
thousands, 600 billion, 851 million, 475,143. That's bigger than an integer can store. Does anyone know how to algorithmically determine the prime factors of a number? Let's talk about it. This boils down to a concept known as the fundamental theorem of arithmetic, and it amazes me that people have reached college in this day and age and don't know what the fundamental theorem of arithmetic is. The name says everything. It's the basis of mathematics. This is something that should be taught early on. So we have a number like 13,195. We want to figure out what its prime factors are. Every number is made up of a unique product of primes. If we wanted to write out something like, starting with the number 2, what is the product of primes that gets us to each one of these numbers? This would be just 2, just 3, just 2 times 2, just 5, 3 times 2, 7, 2 times 2 times 2. Do we notice how each list is unique? This would continue forever. Every number can be broken down into a unique product of primes. This is the fundamental theorem of arithmetic. So if we wanted to do this algorithmically for something like 13,195, how could we do this? Would a process be that would identify what this list of numbers is? Hint, here's the list of numbers, but how could we go figure that out? I want to include 9 just for a second, because it's going to be important. What do we notice about all of the numbers that contain 2? They're divisible by 2. Does that seem like a reasonable thing to start checking? Starting with the smallest prime, is this number divisible by that smallest prime? Is 13,195 divisible by 2? Will 2 appear anywhere in the list of its product of primes? Ever? No. If it were, then the original number there would be divisible by that prime. Is 13,195 divisible by 3? It is not. The easiest way to determine if it's divisible by 3 is to sum the digits.
Oh, yeah.
And if you sum the digits and the digit sum is divisible by 3, then the number is divisible by 3. Random hack. 1 plus 3 is 4, plus 1 is 5, plus 9 is 14, plus 5 is 19. Is 19 divisible by 3?
No.
No, so 13,195 is not divisible by 3. So that can save you a little bit of time in the remaining 2 or 3 times in your life where you're going to be asked if a particular number is divisible by 3. So the algorithm for this is going to look like starting with the smallest prime number, 2. Is the smallest prime number, is that prime number divisible? Does the number divide that? If it is, ask the same thing again, because we don't want to move on to the next prime until we've exhausted the number of times that a particular number is divisible by that prime. So for instance, 8, we need to ask, is it divisible by 2? Then divide it out. So the number we'd be working with is 4. We see how 8 is made up of 4 times 2, so this product of primes times 2. So we need to continue to ask, is the resultant divisor divisible by that same prime? Once the remainder is not divisible by 2, move on to the next prime. Ask that question. So if we were doing 6, for instance, is 6 divisible by 2? Yes. Divide it out. Now the result is 3. Is 3 divisible by 2? No, so we move on to the next prime. Is 3 divisible by 3? Yes. How do we know when we're done? When the number that we're trying to divide is 1. 3 divided by 3 is 1. Is 1 ever going to be divisible by another prime? No. So we're done. Does that process make sense to people? So what we would do if we were trying to figure out 13,195, let's say we wanted to do this, we ask, is 13,195 divided by 5? It's 20 per 100, so we have 131 times 20, which is 262 with an extra 0, so 2,621. I'm close-ish. What's the actual answer?
2639.
2639. So that's the new number we're going to use. So rather than generating the next prime, we're going to try this again. So now with this number, we're going to say, is that divisible by 5? And no, so we're going to generate next prime. And that's 7. We're going to continue this process until the number that we're working with is 1. Once the number that we're working with is 1, then we are done. And we know because of the fundamental theorem of arithmetic, we will always get 1 at the end. Eventually, we're going to end up with some prime number. We divide the prime number by itself and we get 1. Does the algorithmic process make sense? So this is the program that we want to write today to try to solve this problem for a number that is much larger than 13,195. Before we start, let's go through a little bit of a planning process. One thing that people are going to need to know, we can't store this as an integer, so what should we do about it? I think I might have hinted at what we want to do earlier. Make it a long. Yeah, so we do something like long num equals 6008514751443. And then at the very end of this, we need to make sure that we include the letter L before our semicolon. The L just means store this number as a long, represent it as a long before you put it inside of the long variable. Otherwise, you'll get some kind of error, but make sure there's an L at the end of that, and this will allow you to internally represent this number. And you can still do all of the same things to the long that you could do to an integer, like divide it. All right, so next, let's start to brainstorm what methods or what tasks we're going to need to be able to do this. What English names do we think we're going through this process? What are we going to need and what should we name our methods so that we can start to implement this kind of piecewise, a little piece at a time, rather than trying to start at the very beginning and do all of this all at once?
It's gonna be like recursion. I was thinking, when I was trying to solve this problem, I was trying to find all the prime numbers all the way to that, and then grab the number divided by that, and then to the next one, to the next one, to the next one.
Okay,
But that was like a very lengthy process, and I couldn't figure it out.
so there are going to be quite a few primes. And I guess we could store this as an array list so that we could grow it on an as needed basis if we needed to do this. If we were to do this, this is an intriguing mathematical thing that people should probably know. How high up would we need to go? How far, when could we stop? All prime numbers, what is the largest possible prime number that could go into this? The square root, that is the correct answer. So if you were to loop this, you would need to identify the square root of this and find all primes from 1 up to the square root. You will not need anything larger than the square root. Does anyone have any intuition as to why that is?
The square root is going to be number, it's like 5 squared is 25 or whatever, except it's gonna be ginormous number, which I do not feel like calculating in my head.
Yeah, so I like to think of this in terms of rectangles for some reason. Whenever we have something that divides into it, there's always 2 numbers that are associated with it, right? Like for instance, 8 is made up of 2 times 4. So when we find some of the factors out of it, there's the number that we're dividing into, and then the remainder, and you multiply those together to get the original number. So you can think of drawing a rectangle where the length times the width ends up being the area that represents that number. So for 13,195, we ended up with the first rectangle that we found was one that was 5 by 2,639. The area of this rectangle would be 13,195. What is the shape where you minimize the perimeter to maximize the area? It's a square? It is. So there's no reason to go past the square root of a particular value, because you might say, well, this number could be larger than that, but it's going to be the flipped rectangle here where we have 5 on one side and 2639 on the other. If one of these is larger on one side than the other, then we would have found it by dividing the other thing with another number before the square root. So that's the intuition behind why we only need to go up to the square root. We only need to find edge lengths up to that which would be the square, where the area is the final value that we're trying to calculate. I don't know why I think of it that way, but that's how I visualize why we only need to go up to the square root. Okay, so we could do that. But we also might not need to go quite that high. What is the square root of 13,195? Someone who has a calculator out. $114, some point something. 0.8. So we would only need to go up to 115 or 114, since it couldn't be anywhere between 114 and 114.8. How many primes are there between 29 and 114? A good few. So I'm not horribly concerned with efficiency in this class as much as I am in data structures. So we could very well just generate all of the primes up till that point and then just start doing that. That would perfectly work. If that makes the most sense to you, you're welcome to implement it that way. So maybe in that case, we're gonna write a method that is called generate primes. It's gonna take some value, probably a long, since we wanna know up till what value. So we want to pass in the square root of something. And it's gonna return some kind of list. I don't know if we should make this an integer or a long. We'll say integer. We'll modify this if we need to. Let's call it primes. So we would just need to implement this to generate a list of primes to check. And then we'll need some kind of logic to go through and do the rest of this. So are there any other, what other methods would we need in there? So generate primes is going to give us the list of primes. Given that we have the list of primes, do we need any other logic that would help us prepare to solve this?
Would that be add, like, once we find that number, add into this list?
Yeah, so we're inside of this, we're gonna make an array list. We're going to go through some logic that's gonna fill it with all of the primes between 2 and whatever we pass in as the upper bound of what we need, which is gonna be the square root of the original number. So if we were trying to answer this for 13,195, we would pass in 114. And then this would return an array list of all of the primes between 2 and 114. I think inside of this, we're gonna need something that tells us whether or not a particular number is prime. Because we need some way to fill this list. And unless you happen to have the list of primes up to the square root of 600 and something billion memorized, we need something algorithmically that's gonna fill up the list of primes for us. I think if you implement this and you implement this, then we should be able to write some kind of driver that uses these two tools that does this work in a loop. So let's start. I know we're already a good chunk of the way into this class, but let's start by just writing these two tools. Don't worry about the entire problem yet. I would even start here. This is the easiest, simplest way to determine, is a number prime? Generically. How do we figure that out? So we need to figure out if there's any other divisor of that number. How far up do we need to check for that? Square root. So this is kind of a weird subproblem of that problem that kind of looks the same. So if the query is 11 prime? We only have to go up to the square root of 11 to figure out whether 11 is prime or not. If it doesn't divide anything by the time we get the square root of 11, then it is prime. So start with this method, and as always, let's pair program for this. So find someone you want to work with nearby. Can be the same person as last time. If you want to, you can get up and move around, find someone you don't know, introduce yourself. I know that's a scary concept for computer scientists. I don't let too many opportunities to bash my major go by. When you finish implementing this, implement generate primes, which we'll call is prime, so you don't need to redo this work, just call this method inside of a loop to generate the primes up to this value. So you're just going to go up to this value and you're going to generate all of the primes. Whenever this returns true, add it to the list. Once this list returns, you're ready to start thinking about this logic. And it will be a lot less intimidating if you already have the tools in place so that you can just call these methods. Each one of these shouldn't be horribly long. All right, you have about 30 minutes to finish it off. Let's see if we can do it. Does everyone have the number written down that they need? Am I free to start thinking about the coding of this? I'm moving too fast. How are people doing? Who's finished his prime? One person. Who's finished generate primes? All right, good to know. Close. Who is stuck? People are stuck. Raise your hands. All right, so here's my implementation of is prime and generate primes for those who are stuck. Yeah,
Why were we using two instead of one for the I?
because one is not prime by default, and one is gonna divide everything.
I guess that makes sense.
So we don't wanna either add it to a list of primes because it's not prime, and we never wanna check whether a number is divisible by one, because that's not gonna do anything useful for us. So upper bound is just it's gonna end up being the square root of the number that we pass in, because we only wanna generate primes up to the square root because of the square logic that I had here.
Do we have to test this over, is it I is less, or should it be less than?
To the square root. I guess if it ends up being an integer, if the square root happens to be an integer, we probably do want to say less than or equal to. You are right. Do that here, and I'll do that here. That is a good point. If it's not an integer, then we're okay going less than. But if it is an integer, we want to make sure we test that as well.
Or is fine,
Hmm?
I think it's fine, return all sketch back into this tree.
Oh yeah, I did flip that, didn't I? Ah, if it's divisible by something, then this should certainly be false, and then if it isn't, then it is a prime, so it should return true. Thank you. Yeah.
I flipped it and then I was like.
Wait a second. This is what happens when I write things a little bit too quickly and don't check my work. Good. If nobody caught that, I'd be a little concerned. Good job.
I kept running it and I went, this seems to be wrong. 3 is showing up as not prime.
Everything that's prime is not prime. Everything that's not prime is prime. I wonder what I did. That is funny. All right. So hopefully this helps people to get unstuck on whatever it is that you were working on. Does the logic of both of these make sense? Now that they're actually correct? All right, with the remaining 15 minutes of class, let's see if we can come up with the main logic here. And really, these should both be static because we're going to write a main that uses these as well. So the goal now is to, in this main, write this logic. Well, I don't even know if we want to do it in the main. We probably should just have like some other method that we're going to call here for this, but. Let's actually do that. So those should be the two lines of main. Not very much. Identify what the number is, and then print out the call to calc largest prime factor. And this would allow us to factor this logic out so that we could make, for instance, a list of queries and pass each element of that list of queries on to calc largest prime factor and get a bunch of received facts. So let's throw this logic inside of calc largest prime factor. How's it going for people? Anyone have it solved? Laptop batteries, am I right?
Blackberries last ridiculously volatile, even if you try to drain it.
It's because they have no computational power.
Also, Linux is also supposed to type of nightmare.
That's valid. Anything that uses less energy. Windows as an operating system is just the bulkiest. Let me run this and test it. Hey, I think that's right. Nice. I have an answer too, so I'd be curious to compare and see if it's the same. Seems like the amount of pair programming that happened here went down considerably. I see a few people working together. How are people doing? Is anyone stuck to the point where you're not making any progress? Close, yeah. So that people have time to write an answer and calculate it. This is what I'm getting. Here's my calc largest prime factor. And an answer. I think that's correct. On to ask me that L at the end, so that knows otherwise it prices for the jury goes, can't do that, there's not enough space. Yeah, 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 there's an L right there. Yep, yep, nice, nice. Glad you got it working. Does everything about the solution make sense to people? Is it along the same lines as what you were working on?
Could you explain how you decrement the current value within the while loop?
Yeah, so this is just this concept of, well, let's say we had 8, where we want to look at 2 multiple times, because 2 goes into 8 multiple times. So this loop is just saying, while 8 goes into 2, which 8 will always go into 2, but current value, once we see that 8 goes into 2, we want to divide 8 by 2 to get 4. And then current value is now 4, which also divides by 2, which gives us 2. 2 divides by 2, and we get 1. So now we break out of this while loop, we see the current value is 1, and we return the largest value that we got while we were going through this, which in this case was 2. Once we divide a number out, we no longer care about where we came from. We don't need the 8 anymore to figure that out. So we're just kind of saying we're going to be dividing the number by each prime that we get, turning this into a smaller number, smaller number, smaller number, smaller number, making the problem a little bit smaller, a little bit smaller, a little bit smaller, until we end up with some number that is prime. The largest number that's prime, when you divide it, it is 1. Does that make sense?
Yeah, that's right, because if it wasn't divisible, we just continue to use that part.
Yeah, exactly. So we just have to iterate through the list of primes that we calculated and generate primes, and we just use the next one and the next one until we end up with the current value is 1, in which case we know we found the answer. The last thing that we set largest prime to is going to be the largest prime of the whole thing. So I will also upload all of these. I know I haven't uploaded the first couple that we've done, but I'll try to upload each of these solutions as well, so that people can play around with them if you'd like. Almost fully better. I tend to cough for weeks though so I may be doing this for a while. All right, we are out of time. I will see you back on Monday as we go back over the latter half of the strategy pattern. Hopefully this was fun and useful. Yeah.
You're left, you want us to have the interface in our package, or
No,
that iterator, sorry.
Yeah, you can just completely get rid of it.
So you just want doubly linked node, singly linked node, link them both, all 3 on the list.
Yeah, singly, doubly, and circular.
And then that's it, you don't need the driver or the iterator.
Yeah, so I want the nodes as well. Yeah, you don't need the driver. Singly linked node, doubly linked node, I still want that in the
Oh, yeah,
database.
yeah, yeah.
So yeah, the nodes for the lists, no iterator,
no.
no iterator.
Is it okay if we package it all?
Yeah. Yeah, totally, you
I was
can.
like, I can delete it if you want.
Yeah, no, zip it all up. All right. Yes.